Thanks for inviting me. So the topic of the day sounds a bit like old image processing problem, which is super resolution, and even old in terms of algorithms, because the Lucas-Kanade algorithms is something which has been published about 40 years ago. It was actually published before I was born. It's about aligning images, and what we are going to see here is some point of views that allow you to revisit such algorithms in a context which is much more modern. So let us go directly into the topic. So it's what I'm going to present is something that was published at ICCD last year. It's actually joint work with Bruno, Lecouat, and Jean Ponce. So Bruno is our PhD student who conducted most of this research. And so super resolution, you may know about this problem. It's about taking a low resolution image and applying some technique that can rely on machine learning to produce a higher resolution image. So it's a problem which is very ill-posed, which is actually quite difficult, where very often the goal is to use a machine learning framework that will hallucinate small details.
Could I just say that I think there's a kind of black box on the right-hand side of the screen.
So that's what I was asking about. So that should be better, perhaps. At least the box.
Yeah, it's still there, but it's very small, so that's perfect.
Yes. And so but imagine now that instead of a single signal, single observation, you have a burst of observations, meaning you take your camera, you press the shutter, and instead of taking a single image, you take, let's say, 5, 10, or 20 ones. That will vary a tiny bit because there will be hand tremor, for example, so they will slightly vary with, in terms of viewpoints. So by doing that, you just have more information about the scene. And in that case, there is hope to recover the true high-resolution signal which is present in the data. So that's our goal. Our goal is to process bursts of images. I would say one of the first paper that was on this topic was also about almost 40 years old, but it actually is a very hot topic these days, at least in the smartphone industry with very recent papers. So, and in fact, when you take a recent smartphone, it will already take burst, even if you don't know about it. Okay. So I will do like in experimental sciences and start actually with some results. And then I will talk about the method, about the machine learning which is behind this. So in the previous scene that was on the screen, which looked pretty nice, it was a 20 megapixel image. What you could not see was that if you zoom on it, the quality is not very good. And the reason is that it's a picture that was taken with a low exposure time, meaning that there is not much light that will hit the sensor. And to recover the signal, we have to amplify the signal. And by doing this, you also amplify the noise. So when you look at tiny details from the scene, for example, here, there is lots of information which is lost. So what you see on the left is the zoomed in on one frame that was taken by the camera. So it's actually a very good camera. And even if you ask for high quality settings, this is what you get in this regime, which is called a high ISO setting, meaning the signal has to be amplified to recover something. So you see lots of things are missing. And if instead you take a burst of 30 images, so the camera the data is acquired by hand, meaning that there is a small motion which is unknown. If you process this burst, you recover the result on the right, where lots of the quality is obviously much better. So here is another example. It's another part of the same scene. So what I'm showing here is real data. It's a real scene that was acquired, let's say in the wild. And we recover lots of details that are impossible to see on a single frame. In particular, if you look at the hairs of Elsa here, are well reconstructed. So here is another example. So the goal here is not to promote the use of alcohol for scientific presentations. It's just that it's a scene which is pretty nice from an image processing point of view because it contains lots of very fine details, some text, that is impossible to read on the left, but which on the right is well recovered. Okay. So after presenting you some results on real data, I will now move to what we are actually addressing here. What are the difficulties of this task? What do we need to do to address it? So first question, what is a burst? So the burst is what you see on the right. So you're supposed to see something moving. Could you confirm that you see that moving? Or?
Yep, it's moving.
Yes? Okay, perfect. Okay, so a burst is something like this. It's very noisy, and there is motion, which is just due to the natural motion of the hand when you take a picture. So the challenges are to increase the resolution, and for that we need to align the different images that are in the burst with an accuracy which is below the pixel, such that we can increase the resolution. Then there is another task, which is, well, there is lots of noise in the data, so we have to perform what is called blind denoising. We have just to deal with the noise and remove it. And finally, there is also something that you may know or not about sensors in digital cameras, which is that for every pixel, you actually don't get color information. I mean, more precisely, you don't get full color information on most of the sensors that you have on cameras. What you have, a pixel, is just this a small box, like this gray box, that will count the number of photons that will hit the sensor. So what you have to obtain color information is, in fact, an array of filters that will acquire, for example, the partial color information on one of the RGB channels. For example, here you have some green pixels, red pixels, blue pixels. They acquire only information on one specific color channel. So we call that the Bayer pattern. So that means already, and that may seem surprising, is that when you take a picture and you are happy about the color information that you have acquired, in fact, 2/3 of the color information that is produced by your camera is actually just an interpolation. It's actually simply estimated from partial information. Okay. So the goal of reconstructing the full color information from this pattern of colored filters is called demosaicing. So it's a classical problem, which is not easy. So the task here is to do all of this at the same time. So it's actually a difficult problem. So here is a tiny bit more details about what the camera does to reconstruct the color image. As an input, you get partial color information. Then there is many tasks that are, and actually all of this is just a simplified view about what the camera does. You have what is called white balance, black subtraction, and so on. Typically, you will have a denoising part that will try to remove the noise, a demosaicing part that reconstructs color, and then you have other nonlinear operations that are applied such that what you obtain looks nice on your screen. Okay. So now what you need to remember from this is that these are relatively complex steps. And in fact, dealing with the output of the camera is maybe not what you want, because this process will in fact lose lots of information. Not because the camera is bad, simply because the reconstruction task is difficult. So we should better work with raw data, which did not go into such a process here. So the other point, which is interesting and that will illustrate why demosaicing is difficult, is that this reconstruction task will basically ask for details whose frequency may be higher than the resolution of the sensor. And if I come back to the Bayer pattern here, you see that the resolution for the blue pixels is actually twice lower than the resolution of the image. So that creates some basically aliasing artifacts. And on the right, you will see an example of a burst where there are tiny details in this picture whose frequency is in fact much higher than the resolution of the sensor. And it creates some artifacts that are these bluish or orangish patterns. So this is a typical case in real life of aliasing. So what is aliasing? It's simply spurious low frequencies that appear if you try to undersample a high frequency signal. So it's basically what you learn in signal processing 101, and aliasing is supposed to be bad. So what we typically do is that we add some filters that remove high frequencies such that you don't observe this sort of patterns. But in fact, what anti-aliasing is doing? Anti-aliasing is removing high frequencies, which in fact is bad for our task, because what we are interested in is doing super resolution. So we really don't want to remove high frequencies from the data. So that's actually an insight which was well known in the world of super resolution, at least for multiple frames. Aliasing is in fact something good because it's simply measurements about high frequencies. If you have a single observation, it's maybe an observation which is these high frequencies will be hard to recover. But if you have multiple ones, there is hope to do so. And this is actually what we do. So the task of multi-frame super resolution, there is lots of prior work. Like I said, there are, let's say, methods from I will call the old work that are not based on machine learning. There are methods that are based on classical inverse problem formulations. I will call that the iterative approaches. And of course, these days, we try to do that with deep learning methods. Now, something which is difficult to apply deep learning is the question of training data, of ground truth data. Because if you think about this, what we would need to train a black box to solve the problem will be a set of pairs of bursts of images of low resolution that are associated to a ground truth high resolution. And in fact, it's actually not really possible, or at least it's extremely difficult to acquire ground truth data which is of high quality. The reason is that you would need two devices that acquire the same signal at the same time. It's hard. So basically, there is still something very interesting, is that in recent work, there is a process to simulate raw burst from high quality RGB color images with noise which is relatively realistic. And we are going to rely on this for the data. So we will call that semi-synthetic data. Of course, semi-synthetic data is not exactly real data. So then we will need to have something which is pretty robust, such that even if you train on semi-synthetic data, it will generalize well on real data. And our solution is actually to go in between these two worlds, the world of deep learning models that basically train a black box on semi-synthetic data, and this work of this world of inverse problems that actually model precisely the physical image for the way images are produced, according to the rules of physics. We are going to embed this information into a trainable architecture. So for that, let us start by looking at what we do in the old world of classical inverse problems. When I say old, it does not mean that it is irrelevant. It's just that it's a classical way of doing. What we do is that we look at, okay, what is the relation between the true signal we want to recover, let's call that X, a high resolution image, and an observation YK, so which is one element in the burst. So the relation is as follows, or can be modeled as follows. We take the high resolution signal X here. We are going to warp it and resample it, because there is, compared to the true signal in the burst, remember that there are small motions because of the hand tremor. So we need to estimate some warping operator that we will call W indexed by pk, where pk are the parameters of the warping. There are many ways of modeling that, but here just think, for example, as translations, rotations, or something like that. After you do the warping, then you do downsampling, because from the high resolution, you go to low resolution. So we downsample the signal with some integration operator B. And also because we deal with raw data, we are going also to undersample in the color domain by removing some channels at every pixel. But it's something which is, and of course, you add some noise. So now that you have your image formation model, it becomes natural to write an inverse problem, meaning I have observations Y1 to YK that are different images from the burst. And I will simply write this sort of energy minimization problem where I want to find an image X such that if I also estimate correctly the warping parameters, I get I'll get an estimator here, which is close to the observation. So I have a classical data fitting term. And of course, because the problem is difficult, sometimes it's not well posed, we need to add a prior. So we add your favorite image prior, phi theta of x, where theta may be some other parameters, and we optimize with respect to x and pk. So this is very natural, and there are many ways of doing that. So when I say there are many ways, there is at least one way which is relatively simple conceptually, which leads to basic operations that, that are simple enough for us, that we are going to use later. So let us look at this technique, which is called half-quadratic splitting. The idea is very simple. It's if we look at the previous formulation, it has two terms, the prior, phi theta, and the data fitting term. And here, what this method consists of doing is simply to add an auxiliary variable z, which has to be close to x, such that we have an additional term here with a parameter mu t that is going to grow along the iterations, such that z should be at the end as close as possible to x, and such that we really optimize the previous cost function. Now, when we look at the resulting formulation, there is a specific structure that we can exploit. The first one is to notice that optimizing with respect to the warping parameters pk, for example, there may be an affine transformation of coordinates. If we apply a classical algorithm such as Gauss-Newton to do that, you recover the classical algorithm of Lucas and Kanade. So Lucas-Kanade is basically Gauss-Newton for estimating the parameters, the warping parameters to align two images. And so this algorithm, the good thing is that it's actually something very robust. It's one of the greatest success of computer vision. And because it was a great success, there have been lots of engineering work that has been done to make this work on real data. So that's something which is good for us. The other observation is that minimizing with respect to x, it's a simple term here with the basic quadratic function plus the prior. It corresponds to computing what is called the proximal operator of the prior phi theta. For many priors, they are closed form to do that. And minimizing with respect to z, we just have a quadratic function, so you can use gradient descent, conjugate gradient, your favorite method for minimizing quadratic functions, such that we can simply do a block coordinate descent method to minimize this approximate. Okay. So now,
could I just ask?
Yes?
So what are x and z initialized to?
It's a good question. So how do we initialize this? So it's a good question because overall the problem may be non-convex. So if you fix, let's say, the warping parameters, the previous formulation was maybe convex if your prior was like a total variation prior, so you will not care that much about initialization. But here, what is a bit tricky is that pk may not be, the optimization with respect to pk is not convex. So initialization may matter indeed. So what should be the initialization? It could be any estimate of the high resolution image, for example, that could be obtained by just a bilinear interpolation. You take one raw image, even a single one from the burst, and you create a high resolution color image by bilinear interpolation. It's the most, it will be, let's say, the simplest possible baseline to produce a high resolution image. So the quality is not very good, but at least it's a relatively reasonable estimate for initializing this. Now, I must say, I don't remember exactly what we did in this paper for initializing, but that would be something very reasonable to do. So you take a basic method very fast that gives you a first estimate of a high resolution image. And then you alternate several times. So, but we are still here living in the old world. It's not always that bad, but what we know from the new world is that the new world is actually pretty good at designing image priors. that have parameters, theta, that can be really adapted to the data. And for that, how can we, in this sort of inverse problem formulation, how do we typically deal to add some priors that can rely on training data, or that are at least introduce some learning? And the first idea was introduced in this paper from 2013. It's called the plug and play prior method. It's something that looks very strange at first, but there is still some good intuition about it, I think, which consists of saying, well, how does the prior impact the algorithm? The prior impacts the algorithms through these optimization steps. So that was, if I come back to the previous slide, it was the optimization with respect to X. It corresponds to solving a problem like this. And this is called the proximal operator of phi theta here. So the effect of the proximal operator is actually to make a current estimate Z that will be, let's say, compliant with the prior. So in a way, it can be seen as some sort of denoising step. We want to have X which is close to Z, but we want phi theta of X to be small as well. And for denoising, it turns out that classical deep learning models, such as convolutional neural networks, are pretty good at it. So the idea is that within an optimization method, replace the proximal operator by something like a convnet, which depends on model parameters theta. Now, this gives you parameters. So the natural question is, well, we need to learn them in some way. And then comes the second idea, which is bi-level optimization. So what is bi-level optimization? It's a way to write, it's basically an optimization problem that involves two objectives, one which is called the outer loop objective, one which is called the inner loop objective. And what we have here, we have here a learning, let's say, a loss function for learning the parameters theta. Where what do we have here? We have training data, which are pairs of high resolution images xi, bursts yi, and in the inner loop, we have an estimator x hat theta of y. So we take as input a burst y. We have model parameters theta, and we call the resulting estimate that is obtained by optimizing this cost function on the bottom right, which corresponds to the inverse problem. We call that x theta of y. Now, the question is, how do we learn the model parameters theta? So, well, we do that by minimizing, by making sure that x hat theta of yi is close to xi. Turns out we use the L1 norm here. We could use another norm. It remains a bi-level optimization problem. So basically, bi-level is we have an objective, and one part of the objective depends on a solution, or if the inner loop problem is strongly convex, of the solution of the inner loop. So it's typically something which is a bit hard in terms of from an optimization point of view. But conceptually, what is nice here is that we have an inner loop that solves the classical inverse problem that involves model parameters that are trained such that the output, the solution given by the optimization procedure of the inner loop produces good solutions. I don't know if it was clear enough. So basically, it's these ways of dealing with two objectives, and there are many, these days there are more and more applications of bi-level optimization in machine learning. So the most common application, I think, is about hyperparameter optimization, where we have, let's say, hyperparameters that you want to learn. You have an estimator that depends on these hyperparameters, and you want to make sure that these estimators does well on some validation set. So here it's a point of view that also appears in image and signal processing, but let's say in the machine learning world, it's more common to have this for hyperparameter optimization. So now this is how to optimize. So how do we deal with it? Well, the last idea is something that was introduced in the context of sparse coding about 10 years ago. Is the concept of unrolled optimization. So unrolled optimization is conceptually simple. we consider the previous optimization procedure for solving the inverse problems, you know, that produces an estimate x hat theta of y, but we stop it after t steps. So which gives you an estimator that we called x hat theta t of y. So given a burst y, we have basically this optimization method that produces an estimate. And the idea of unrolled optimization is to see this sequence of optimization steps as a computer program that allows to do differentiation. So we will see every step of the optimization procedure as something that allows to do backpropagation, basically. So that makes basically this old world of inverse problems compatible with any deep learning framework, such as PyTorch, for example. And you can basically now consider this optimization problem here that is well defined. You can see this x hat theta t of yi as some, let's say, network architecture that produces a high resolution image. And to make sure that on training data, you can minimize this. So at the end, this gives you something. So I don't really like this way of describing algorithms, but if you like, you know, algorithms that are seen as a sequence of boxes, we have basically an architecture that takes as input a raw burst of images. At the output, you get a high resolution image, and in between, we have steps that are interpretable. We have some of them that apply the CNN that removes, you know, which is this plug and play prior. We have the Lucas-Kanade steps that perform alignment, and the challenge would be to do backpropagation through all of this. But the good thing will be that it works pretty well on real data. But I showed you that already at the beginning, results on real data. And to show a bit as a proof of concept how far we can do, at least on synthetic data, here is an example where we do something very unrealistic in real life, which is extreme. We take RGB image of high resolution, and we randomly generate some low resolution images with some burst, with some random motion. And then we apply this to our method. We try to see if it can estimate correctly the motion and perform the high resolution. And this is what we obtain. So I hope that my internet connection is not too bad, such that you see lots of details. But basically, from 20 images that look like this, that are very bad, we recover something like this. So of course, this is a bit extreme. We never do times 16 super resolution in the real life, but we do other things such as this. And it's time where I will actually share just the website, because we have a website that have results that look much nicer than this. So I'm going to switch to the website. So question is, do you still see the slides, or do you see a website?
The website flashed up briefly and then it went back to the slides.
Okay, so let me stop sharing and share again. So here you should now see the website, right?
Yeah, that's working. Okay,
so it's just a few examples. So we applied this on several smartphones, so Pixel 4a, Samsung S7, but that are not super, that are a bit old, also on my Panasonic camera. And this is the types of results that we obtain. So far you see two images that look similar on the right and on the left. On the left, you have a 20 megapixel image. On the right, you have a 200 megapixel image. And if we zoom, let's say I zoom here. On the left, you see what the Pixel 4a camera produces from a single frame. And on the right, you see what we have reconstructed. So it's a typical case where there is lots of aliasing and these moire artifacts on the left that we recover. And there are lots of other parts that are, the results look quite nice. Let me see what we see here, for example. I know you see these antennas that are well reconstructed. The part, let me look at another part, which, yes, this part looks nice. Simply because you see, for example, that on these windows on the left, you don't see any pattern, but you see the horizontal stripes on the right. Plus this, all of this reconstruction of I mean, there are many details that are well reconstructed here, and we kind of like these results. So let us look at another one. This one was actually, so if there is no lag, you should still see, this is the picture that I showed at the beginning, you know, where we see the text on this bottle of rum, or, you know, on this one, we see lots of details that are well reconstructed. Let me see if I have another image that looks nice. This one is nice. It's taken in Paris. It's actually in the Jardin des Plantes. And if we zoom very hard on this part of the picture on the left, you see that there is some text that is maybe 2 or 3 pixels high and it's impossible to read. On the right, if you are French, you should be able to read "Cet arbre a reçu le label Arbre remarquable de France." I'm not sure you can read that through Zoom, but if I was in person at UCL, you would be able to read it. Okay, let us stop. And anyway, this website is public, so if you want to zoom a bit on the other details, feel free to do it. What is, I don't remember exactly what is this one, perhaps not that interesting. Yes, okay. So let me come back to the slides. And or perhaps these extreme time 16 super resolution examples, they are a bit, you know, they should not be considered as real data, but still they show that even if the motion from the data was random and unknown at test time, we are kind of able to recover very fine details. Okay, let us come back to the slides. Slides are here. And here, so that's why I wanted to show you this on the website. So here, that was another example from a picture where we can recover the text. And on the next one, there were, again, extremely tiny patterns that were impossible to see in the middle that we see on the right. In terms of quantitative experiments, it's not that interesting for this presentation. But it's actually relatively difficult to evaluate the quality of results quantitatively on real data, simply because, like I said, at some point, we are dealing with problems for which ground truth does not exist because it's impossible to acquire correctly. And even, you know, for the simple denoising task, you could imagine that denoising is a simple problem, that acquiring real data is easy, but in fact it's not. You can, for example, put a camera on a tripod and say, let me take 2 images, one which is noisy with low exposure time, one which is not noisy with a long exposure. You can do that, but even if you have the best tripod in the world, or let's say not the best tripod in the world, but let's say a quite expensive tripod, there will be misalignments between the 2 images just due to the natural, you know, motion that that is in the ground. You know, that there you have some small vibrations that will simply misalign the images, such that in your ground truth you will have a noisy image, a clean one, and you cannot just use, you know, L1 norm or L2 norm to compare them because they are not well aligned. So that's why this image processing is not easy. So in the past, in the first version of this work, we also had a few issues that were due to the model that we used, because the model was assuming that the scene was static, such that if in your burst you had motion, you will see ghosting artifacts like this. So since then, we have solved this problem, but I cannot show you some results at this point, simply because the results are there, but we are writing a patent about this, and it's not public yet. But soon we should be able to show this and show more results. So the take-home message from this, there are several ones. One of them is that, well, there is lots of very nice work in the old computer vision literature with algorithms that are robust on real data, interpretable. In fact, we can revisit this line of work with differentiable programming principles, such that we can add a bit of learning to these methods. And something I have not mentioned as well is that one of the nice things about this approach is that, you know, are interpretable in the sense that part of the architecture does some steps that we can describe mathematically. They are, you know, optimizing, they are aligning. Doing that at the end produces architectures that are pretty light, which does not have many parameters. And this is important, in fact, because for this super resolution task, we made some comparisons with state-of-the-art approaches that were based on just, you know, a big deep neural network with attention layers that had 26 million parameters. We could do as well with only 300,000 parameters, only because we don't ask the model to learn what we already know about the task. Meaning we need to align. So let us use at some point some aligning algorithms within the architecture. In terms of current work, we have done some high dynamic range imaging work, which for the same reason as before, I cannot show you the results, but I would be happy. It's something that at some point we will add to the website. Deghosting was doing some improvements to deal when there is some motion in the scene, something we have done. Something we are currently working on is also the problem of focus stacking, which consists of dealing with images that are a focus at a different place. The goal, for example, is to do macro photography where typically the depth of field is very small, such that you have many images that are sharp on a tiny part of the scene, but and then the idea is to combine all of these to produce a scene which is sharp everywhere. There are other challenges, such as we want to add deblurring to this. For example, we may want to deal with deblurring, which may be due to the optics. Something that I really would like to do at some point is also to deal with other types of blur that are due to atmospheric perturbations. Nothing which is relevant to any of the images I have shown you here, but something which is very relevant if you want to do astronomical imaging, which is also relevant if you want to do telephoto photography, telelens photography, because let's say you go to some mountains, you take a picture with a telelens on a different mountain. There is, let's say, easily 10 or 20 kilometers of atmosphere. It creates lots of perturbations. And there is some nice work from the old work of inverse problems that address that. And it's something we'd like to address as well. But more generally, there are also perspectives in scientific applications where the goal is not to design a machine learning method that will hallucinate details, but really applications where we are interested in recovering the true signal which is in the scene. And I will stop here. If I had time, I also had a few other things on, but I will maybe put the slides online if you're interested in that. Just to say that this idea of revisiting classical approaches with deep learning principle is very powerful. We have other types of work with nice results here for single images. And that's it. There is also many challenges that are related to this bi-level optimization problems from an optimization point of view. There are challenges from a statistical learning point of view, because these are some estimators that are not very standard, and that's it. So I will be happy to take any question if you have some.